Uh, Hi. In this session, we're going to learn about how to generate VLE curve, Vapor-Liquid Equilibria curve, or to be more specific, Isothermal VLE, Isobaric VLE, and as it is the equilibrium curve, that is X versus Y, that is mole fraction of the more volatile component in the liquid phase, mole fraction of the more volatile component in the vapor phase. I am speaking with respect to the binary liquid mixtures, specifically organic mixtures, something like that. So generally now in this session, I would like to generate vapor liquid equilibrium data or curve for mixture acetic acid and water. So I start a new session. As it is, I start a new steady state simulation. If I am starting new steady state simulation, I will be getting, or you might be seeing this simulation configuration wizard is open. Now there is a next button at the bottom. I take acetic acid. I type acetic acid in the search box. You can see it is added here. It is shown here, and the source database is ChemSep. The formula is CH3COOH. And if I check this box, click this box in the added compounds, now you can check acetic acid is added. Now the next compound which we want to add is water. So acetic acid water is also a very well-known liquid mixture which we find in many chemical process industries. So now you can see the acetic acid and water are the added compounds. Now I go to the next. Now it comes to the what you call property packages. Generally, when there is a water involved, we choose NRTL as one of the package. Okay. See, in the what you call, you can say in our help of the DWSIM package, you can find, you can get a good judgment, or there is a methodology given in what way we can select the thermodynamic package property package based on the mixture properties. Now I add this and then I take the VLE here and then I go to the next. Now this SI system, I go to the C5 wherein I can change. I'll keep temperature as in centigrade, pressure instead of putting pascals, I'll take it as atmosphere because we can say standard is bar, but I would like to take it as an atmosphere when it is convenient for us to just speak out 1 atmosphere, 2 atmospheres like that. And mass flow rate is kgs per hour, molar flow rate is 100 kilomoles per hour. These all other things are, we'll retain the same thing. Now I go to the next. Now this activate double click to open should be activated. Now if I don't activate, it will be like gray color. If I activate, it will be blue color. And then I go to the finish section. Now I'm in the finish section. Now, so immediately see, where will I find the application of this particular vapor-liquid equilibrium curve? So it will be helpful for me to design a distillation column. Okay. So what I'll do, I go to the column stage, I take shortcut column here and I drag and keep into my, this particular area. So, and suppose let me check the documentation. What is my DWSIM in this place? It is 8.4.3. Okay. I have taken a shortcut and I just adjust these particular particle streams, energy streams, and these things like this. Done. So this one I will just rotate so that it looks nice as if it is adding, we are adding the stream connection to this particular reboiler. Reboiler is at the bottom and I hope you are able to see the column here. Now this is the column. So let me adjust this also so that it will be all compact at one place. You can be able to see the total distillation column. This is known as shortcut distillation column. But what is our intention at the first stage? I click on stream 1 and I name it as feed and let us take the number of moles as 100 kilomoles per hour, and then 100 kilomoles per hour, and a temperature I'll keep it as 25 degrees centigrade, pressure as 1 atmosphere only, and compound amounts, but it's a 30 acetic acid, let me take it as 0.330%, and water I take it as 70%, that is 0.7. So I accept the changes. So as it is, you can find the color of the feed stream, which was actually before red, now it has converted into blue color. Now, what is that we are trying to generate? We are trying to generate vapor-liquid equilibrium data. So what should I do? I should go to flow sheet analysis? No. I should go to utilities, add utility, and then you will come to this particular window. In this window, object type, select material streams first. In the utility type, select binary phase envelope, and select flowsheet object. So this is the entire, operation or the selection part you have to do. Go to the utility. I'll do it again. So we are going to generate the VLE data, VLE curve. You should go to the utility, where in the menu bar you find file, edit, insert, tools, spreadsheet, dynamics, and then utility. And add utility here, and go to the material streams, and go to the binary phase envelope and select feed, and then say add utility. So this we have come up to this particular add utility place. We have come to the add utility place. In that, number one, see, compound one is acetic acid, compound two is water. But see, you should be very careful. Compound one should be the more volatile. So compound one, acetic acid, water is more volatile because it's boiling point 100, and acetic acid boiling point is 105. So we should be careful enough. What are we trying to do? Okay, what are we trying to do? So this is what. So now in this place, what do? I check this one, and the mole fraction, 1 atmosphere, temperature degree centigrade, and the step count is 40. Obviously, step count is 40. Now you should take it out like this, because you will not be able to see. Now I have taken out like this, and then let me actually adjust it again. Yeah. So 1 minute. Yeah. Now in this place, if I just drag it and then try to just keep up and down, we should be in a position to check available. What we want is to check the calculate button in this. Yeah, now you see it will be open. Now these all things are ready with us, and I have taken compound 1 to be as water, compound 2 to be acetic acid, right? I am generating Txy data. So what you should do, I should say calculate. Once I say calculate, it is giving me the calculation, and ultimately the vapor equilibrium data is available in this particular place. This can be observed. This is the graph. So this is the graph here. If I want to just show point values, if I click on show point values, you go to some place, you will get the point values like this. Oh, probably it has to show point values. Show point values. Why? Now see, it is showing point value. I have not clicked it thoroughly. Now these are the point values, right? So if you see the temperature here, if I go to the top at the exactly at this place, it is showing 0 mole fraction. Temperature is 117.885. It is actually representing acetic acid, water. See, this is compound 2. So it will be 117 is the saturation temperature of the acetic acid. And if you come to this place, this is 99.99 exactly nearing to 100 degrees centigrade. Mole fraction is mole. What is the more volatile component I have chosen in this particular simulation? It is water. So at the bottom x-axis, what you see is the mole fraction of the water in the both phases, liquid phase as well as vapor phase. What is the beauty now? What we are trying to do? See, in the pressure, see, if I am operating at pressure, the temperature what I have to reach, I may have to reach in the distillation column is up to 120 degrees centigrade. I don't want to do that. I want to operate this in vacuum, suppose say. That means pressure 0.8 instead of 1 atmosphere. Click this, and then I recalculate it, and then now check what is the change you find here in the diagram. The saturation temperature of acetic acid is changed to 110, and saturation temperature of the water has come down to 93 degrees Fahrenheit. Centigrade, sorry. So still more, if I want to operate this as, still more at 0.6, and then say calculate, and now you see it is much less than we are coming down and trying to operate. But these are only, simulation wise. If I increase the pressure, instead of doing that, increase the pressure to 5 atmosphere and then calculate. Now you can see the change in the boiling or saturation temperature to 180 degrees centigrade, and the what you call boiling point of water has reached to 152 degrees centigrade, which is really unoperable. So I let this operate it at vacuum instead of operating at a higher pressure. Once we have generated, okay, let me come back to 1 atmosphere here, and then let me understand the diagram. If you can see the diagram here, water, acetic acid, P is constant 1 atmosphere. So this becomes the isobaric VLE curve. That means temperature is in the y-axis, and x-axis you find the mole fraction of the water in the liquid phase as well as in the vapor phase. Now you see, now the next part what I want to calculate is, suppose I click Pxy, not Pxy, now this is this. I calculate T of xy, and then again I say calculate. It has to calculate and give it to me. It is again giving the calculation to me. This is only x versus y data. But whereas we said pressure is constant. Now if I say P versus xy, again I say calculate. Now this is the P versus xy data for the acetic acid water, but you can see the the curves which have been observed. Okay. Now the I am keeping temperature constant now. See, if I generate P versus xy, it is known as isothermal VLE data. So in the same simulation, I am trying to generate isobaric VLE data, isothermal VLE data. But what is that you have to assume or we have to learn is that how to find the saturation temperature of the individual component. If it is not a mixture, if it is a pure component, what you have to do. With this, I hope you have understood how to actually generate the Txy data. Suppose say again I want to come to the Txy data, again I want to calculate. Now I want to see the table. Now you can see the table here. So this is the entire table. Now you can see X, NRTL X, and then every other data will be available here. You can actually check it. So this is the generation of the VLE data in DWSIM for a compound, for a mixture. What I have shown you, this is acetic acid and water. The property, what are the compounds we have chosen? Acetic acid and water. What are the what do you call what is the thermodynamic property package I have chosen? What is the thermodynamic property package I have chosen? NRTL. Okay. What are the system of units I have chosen? It is C5. That means I have changed the pressure unit from the pascals to the 1 atmosphere. Okay. Temperature I have written it at 25 degrees centigrade. Excellent. Right. Then I have gone into the utility. I have taken a shortcut distillation column because we use Vapor-Liquid Equilibrium data for designing a distillation column. So I have chosen a module called shortcut distillation column, and I have dragged into the flowsheet window, and then I've given the inputs of the feed stream. I have taken input to be as 100 kilomoles per hour, and acetic acid I have taken, acetic acid and water mole fraction I have taken, and acetic acid as 30% and water as the 70%. That is what I have done, right? Then what I have done is I went to the utility in the menu bar and then add utility. In that I have taken material streams. In that I have taken binary phase envelope. In that I have taken the what you call feed stream, and then I try to generate I think rest of the things we need to practice a little bit. So this is what is this session about: how to generate vapor-liquid equilibrium curve. Here, in this particular system, what we have seen, acetic acid and water, it is forming an azeotrope. That is what is seen clearly in the curve. If it is a isobaric VLE data, we are seeing the curve like this and then like this. That means there is an azeotrope at this place. If it is isothermal, that means pressure, it is going like this and then like this. And we need to understand which is the bubble point curve, which is the dew point curve with respect to the Txy curve, and we need to understand what are the bubble point curve and what is the dew point curve with respect to the Pxy curve. That is what is the learning strategy. Okay. With this, I end this video. We'll again look at another systems in another video so that you can better understand. Thank you very much.